The scaling of artificial intelligence strikes the physical limits of the terrestrial power grid long before it reaches the limits of silicon. This graph traces standard data center power against projected AI requirements, showing a vertical climb to over 1,000 terawatt-hours by 2026. Capital can't accelerate this. In major hubs, interconnection queue delays, the wait to plug into the grid, are stretching up to 12 years. The innovation cycle for a new generation of processing chips takes about 2 years. The physical reality of securing land, securing permits, and laying high-voltage copper takes a decade. The infrastructure required to run next-generation models is physically running out of electricity on Earth. Architects are being forced to look beyond the atmosphere. The Orbital Data Center serves as a direct infrastructure bypass for terrestrial grid constraints. This map tracks a dawn-dusk sun-synchronous orbit. Aligning a satellite's trajectory with the terminator line, the edge between day and night, keeps the hardware in perpetual sunlight. Without atmospheric scattering or the day-night cycle, these arrays multiply terrestrial solar yield by 8. Continuous solar exposure solves the storage problem. Ground-based solar requires massive lithium-ion battery arrays to buffer power through the night. An orbital data center pulls power constantly, routing it directly into the compute cycle. We already generate continuous orbital power at scale. The International Space Station operates on 100 kilowatts of solar energy, proving zero-interruption orbital generation is viable. Moving compute to low Earth orbit provides the power required by AI scaling, but it breaks standard thermodynamics and networking. Executing a large language model query in a radioactive vacuum requires specific architectural trade-offs at the silicon level. This schematic shows a GPU architecture processing the initial prompt, the prefill phase. This operation is strictly compute-bound. It heavily utilizes the processing cores to analyze the user's input, while the memory banks remain relatively quiet. Generating the response, the decode phase, operates differently. Generating each subsequent token is severely memory-bound. It shifts the bottleneck directly to high-bandwidth memory, constantly reading and writing massive cached states. Low Earth orbit is saturated with cosmic rays and solar radiation. High-energy particles bombard silicon structures, triggering single event effects, literally flipping the ones and zeros in the memory grid. Standard commercial off-the-shelf high-bandwidth memory will quickly fail in this environment. Because the decode phase relies so heavily on memory stability, using standard terrestrial hardware guarantees high fault rates and rapid system death. Surviving orbit requires moving away from standard GPUs. Architects must specify radiation-hardened processes, like fully depleted silicon-on-insulator, or utilize novel MRAM technologies that physically resist radiation interference. Because the LLM decode phase is uniquely dependent on memory capacity and bandwidth, sustained space inference requires entirely new, radiation-hardened memory architectures. Generating power in space is easy. Shedding the resulting heat requires a complete structural redesign. A dense server rack must unfold into sprawling radiator arrays. Terrestrial data centers rely on convective cooling. They push millions of gallons of chilled water or high-velocity air across hot components to physically carry megawatts of heat away from the silicon. In a vacuum, convective cooling is absent. There is no air or fluid medium to carry the heat away. 100% of the thermal load must be rejected radiatively, bleeding off as infrared light into the darkness of space. This scale comparison puts a standard 1 megawatt terrestrial cooling tower next to its orbital equivalent. Emitting heat as infrared radiation demands an exponentially larger surface area to achieve the same cooling capacity. Starcloud's projections for a gigawatt-scale orbital data center include thermal arrays spanning up to 4 kilometers. That immense surface area translates directly to massive physical weight, which incurs a severe launch penalty. Solar energy in space is effectively infinite, but shedding the waste heat creates a massive, heavy, and expensive engineering bottleneck. Distributed LLM inference requires splitting compute workloads across thousands of chips. Connecting these floating nodes requires terabit-scale bandwidth. Traditional radio frequency satellite links lack a capacity. For data center networking, the architecture requires dense wavelength division multiplexing lasers, shooting high-speed optical beams directly between moving satellites. Optical link budgets are governed by the inverse square law. Laser power drops dramatically as distance increases. To achieve speeds of 1.6 terabits per second, these nodes must fly in extremely tight formations. This is a top-down schematic of Google's Project Suncatcher. It condenses an 81 satellite cluster into a tight 1-kilometer radius, weaving a high-density mesh of optical links. The Hill-Clohessy-Wiltshire equations dictate the physics inside that cluster. Because Earth's gravitational field is not perfectly spherical, these nodes cannot sit still. They constantly drift and oscillate 100 to 200 meters relative to each other. The laser targeting systems must adjust to this drift, while continuous, precise microthruster burns keep the cluster from floating apart and severing the network. In an orbital data center, physical fiber optic cables are replaced by precision orbital choreography. The viability of orbital data centers is measured by life cycle carbon modeling. This equation models the true life cycle cost. Continuous solar power drives operational carbon to zero, but introduces a massive variable. The embodied carbon debt accounts for manufacturing custom radiation-hardened silicon, building 4-kilometer radiators, and the fuel to move that mass into orbit. Breaking Earth's gravity well with heavy payloads of computing hardware requires vast amounts of chemical energy and generates substantial emissions at launch. Achieving scale relies on reusable launch vehicles, like the Falcon 9 and Starship platforms, to aggressively drive down the cost and carbon penalty per kilogram. This chart plots projected launch costs against terrestrial compute costs, indicating a specific economic threshold. Launch costs must drop below $200 per kilogram. At that point, in the mid-2030s, space-based compute achieves cost parity with building data centers on Earth. The final variable is time. The radiation-hardened hardware must survive the environment of low Earth orbit long enough to operate and pay off its initial embodied carbon debt. Offloading AI inference to space enables a massive energy bypass, but it is only sustainable if launch economics improve and the physical hardware outlasts its embodied carbon footprint.